Okay, thanks so much for the invitation. This is a fascinating event. I think there's so much that's coming together here and so much that's important that's changing in the world. So what I want to talk to you about is one particular factor of this whole story. I think we've heard over the last days quite a lot about this, but I'm going to try and connect some of the research we've been doing with this bigger picture. And what I'm interested in is really about this area of miniaturization. So I want to tell you a little bit of technical detail without going into boring detail about our research, but say about what can you do with microfluidic measurements. And I am going to tell you exciting, cool stuff, and I'm also going to raise concerns, things that I'm worried about and things that I think are challenges. The general principle of microfluidics is pretty obvious in a way. It's about miniaturization. It's really about that jump from taking a venous sample with a butterfly and then sending it off to a lab. And by miniaturization, just making our testing process smaller, in theory, we can have miniaturized lab with miniaturized electronic readout. So this is the sort of provocative question, is the future of all clinical diagnostics in your pocket, and can a smartphone really replace a lab? It sounds very compelling, so we'll try and revisit that question. So that's the talk title. We've been through this, but I've got a slightly different take on the why we want to do this. And I just want to take you through the imaginary situation where you're a patient and you're going to see a clinician. You book maybe a blood test, then you go somewhere at some point in time and you sit in a waiting room and somebody puts a needle in your arm. The sample is taken, it goes off to a lab. The labs have got amazing machines, by the way. Some of these machines will give you results in a few minutes. The question is then, why does it take so long to get a result? Because, of course, the sample has to go onto the machine and it has to queue in the machine, and then the results come out of the machine, and then they have to go into some system. Eventually, they get in front of a clinician, hopefully. And, of course, the punchline is when you phone your GP and say, I get a blood sample, what's the result? And then the receptionist tells you what your result is. And then, of course, it's come to you, but then, of course, you're still not in front of the clinician. So on the other hand, the receptionist may book in another GP appointment. So it's a slow, laborious process. So it's incredibly compelling to say, of course, it would be better if when you see the clinician, you do the test and get the result, or even you do the test without even seeing a clinician and the result goes to the clinician you talk to. So you can see this is very compelling. So we have a big red star, fantastic. Point of care testing is brilliant. So, this is what drives this technological development. We're all familiar now with lateral flow tests. I used to have to explain what lateral flow tests were, but we don't need to do that anymore. They are absolutely fantastic because they're mass produced and they're low cost. We know they can be very easy to use. There is strict limitations about their analytical performance. As an analytical tool, they have things that they can measure and things they can't measure. As a result of that analytical limitation, there's also clinical limitations as to what they can do. On the other extreme, you've got your lab analyzers, which are fantastic. They can measure incredibly low concentrations of things with great accuracy. So you've got this kind of one or the other. And of course, what we're trying to do is to develop something that gives you the lab performance near the patient. And I'm also going to highlight this one little technical thing, is that increasingly there's a passionate drive and a evidence that this could be helpful to measure multiple parameters, not just one parameter. So what we mean by multiplex is, instead of one question, one test, one result, one decision, what about if we start measuring multiple things in patients? Surely that we can get much more information that way. I think we all believe that that's possible. So I can then focus the questioner down a bit more. If we're thinking about blood biomarkers, measurement of them, we're interested in panels of biomarkers, and particularly, I'm going to talk in this presentation about molecules detected by antibodies, but that's just one class of blood tests, and we're not using lab instruments. So can we measure panels of biomarkers in a small blood sample in a community setting or point of care in your home? So that's the kind of story that I'm going to give, and then I'm going to try and keep jumping out to try and make more general observations. So the dream is that we have microelectronics in our pockets. Computers are no longer inaccessible, they're cheap, and they are incredibly powerful. So, of course, we want to be able to do the same thing with blood tests and analytical chemistry. We want microfluidics to be partnering with this microelectronics so that we can have point-of-care movement measurements. The specific technology we developed, I just remembered I was going to bring some along, but you're welcome to come and visit the lab, which is just over there, and see this material. It is real. It's a slightly unique or unusual microfluidic system that we use. It's a particularly mass manufactured and very simple type of microfluidics. In essence, it is a panel of 10 test tubes. The test tubes are very small, so each test tube is 200 microns in diameter, or 300 microns. And it's made in extrusion process, which means that we can make it in 10,000 meter lengths. And then, of course, you cut it up. So it's genuinely a mass-produced material, just as lateral flow tests are mass-produced. That's the kind of unique story. And within these tiny test tubes, we can do measurements. So the general process for measurement is you get your sample, you mix it somehow with a reagent, and you get a color change, which is why we can detect it using a smartphone camera. And it turns out that most of these assays can be done in this form. So really what we're doing is we're playing around with the vessel. Instead of using a traditional test tube, we're using a very small test tube. And it's a step forward because, of course, people used to use test tubes. Now they tend to use these microplates where you reduce the volume by 10 or 100-fold, and then we're going to the next size down. And crucially, we start off with this big reel of material. We can coat the different capillaries with different reagents, which is our multiplexing, and then we cut it up into little test strips. So it's a bit like the way that lateral flow tests are made. You have a continuous reel of lateral flow paper and you chop it up into lots of individual tests. So now you have your potential for point of care, tiny little strip, dip it in, do a test, and then you can make these multiple measurements. So, and we can measure all sorts of different things. We have lots of pretty colorful things. Some of the pictures here are from people in the audience who've done fantastic different work. In the middle, we've got some blood tests. So John Gibbons talked about this yesterday. Can we change the way we do the blood tests, that we can make a measurement in a capillary? We've also got some fluorescent assays down here, and this sort of loop here is bacterial colonies growing inside these capillaries, which look kind of cool. So we can measure bacteria on a sort of individual cell basis. So each of those blobs is the equivalent of a bacterial colony growing on an agar plate. So we can translate traditional lab assays down into this miniature format, which seems very compelling. And then we've wrapped it up in various different formats. I won't go into too much detail, but we've played around with using the same material in a lab or maybe point of care or various different setups. We also have an automated system. And I could go and talk you through some data. Essentially, we do a translation of a standard lab assay. We translate that by transporting the reagents into our miniature system, and we get very similar measurement performance. So we can do that with immunoassays. So we wanted to pause for a second and then sort of explain what does an immunoassay allow you to do. And in order to do that, it makes sense to stop for a second and say, what are we trying to measure in blood? And obviously, this is a big, messy slide. I'm not going to go into great detail, but at the top, you've got the biggest things that you measure in blood, typically cells, red cells, platelets. And then way down at the bottom, you've got these things like sodium salts or oxygen. And that's a big range of objects that you're trying to measure. The ones that we measure by immunoassay tend to be in the middle, and they are things like some of the tests that we heard about yesterday and today, things like C-reactive protein. Some of these are defense molecules, some of them are signals that our body makes. We also might want to detect pathogens, so you can detect a viral pathogen. We know that because our lateral flow COVID test is detecting the viral particle. We've also got the new generation of nucleic acid tests. So all of these things are things in blood that we might want to measure. And just one moment of caution is that sounds kind of a bit overwhelming already, but the other thing that I love is this thing on Wikipedia, which is a really simple visual display of things that we measure in blood and their reference ranges. And I've just zoomed in a little bit, so there's all these different things that you can measure in blood, but the really important version is this. So this is a log scale across the slide of the concentrations of these things. So first of all, we've got things that range from whole cells all the way down to individual ions. So sodium ion is different than a platelet if you want to measure it. And then we've got different concentration ranges. And these are the reference ranges. These are the normal ranges that we measure, all the way from really abundant in blood, things that you can almost see because they're so abundant. And then at the other extreme, you've got things where if you take a ml of blood, there'll be a few thousand molecules to detect. So we just need to bear that in mind and we've got to think carefully about how we do this analytical stuff, because if we just say, oh great, we can make this tiny, that's sort of neglecting some of the complexity. So as a result, yes, we can definitely measure these things, but we've got a list of analytical challenges here. You can tell I'm going to be doing this panel conversation about challenges because I've already started to write some of my opinions down here. But we've got this big dynamic range. The targets that we're measuring have different sizes and concentrations. We talk about the matrix. What I mean by that is you take a sample from a patient, it's urine or blood, it's got all sorts of stuff in it, but only one of the things in there is what you want to measure, and all the other stuff can affect your assay. So there's lots of variation, of course. You know, we're all different. We all know that we're different because we all look different, but our blood's different as well. And of course, there's lots of things we can do which have got nothing to do with disease, which can have a massive effect on blood composition. We were having the usual chats about in the lab, when you get volunteers to give blood, you can tell who's had a heavy night the night before because the blood's different. It actually looks different because they've got a hangover. And that's got nothing to do with the disease process. So we have to somehow navigate through this noise of variation. So how does an immunoassay work? So how can we detect this one particular target, which is mixed together with all this other stuff? It sounds like an impossible problem. Luckily, antibodies have solved this problem for us because these are molecules in our body that evolved to defend us from pathogens, but they turned out to be really useful in analytical terms because we can coat them on the inside of our strip. And when we run blood through it, it binds to whatever we want and nothing else. And then we can remove all the blood, so we end up with just the target. We then come in with another antibody, which is labeled, and that label allows us to enzyme amplify, which means that you can get a really vivid, strong yellow color or a fluorescent color. So you can go in 2 or 3 steps from this mixture of blood to something that you're measuring. So that's the kind of thing we're doing in these assays over here. I've got little example pictures of what these look like. These are smartphone images of our micro devices. They're very small, a few millimeters in size. And using these simple steps, we've been able to measure a wide range of different biomarkers. So it definitely is possible, even though it sounds like a big challenge, it's definitely possible to measure all these different things. And in both of these examples, we're measuring 10 different things in a single sample. So the advantages of immunoassays is they are fantastic for analytical sensitivity, and they also give you some sort of washing effect, so you remove all the things you don't want to measure. But the problem is that that makes the assay more complicated, so the big robotic analyzers can robotically add a series of different things and do all of the different steps that you need to do. And the challenge for microfluidics is somehow you have to add the sample, then remove it, and then wash it, and then add the next reagent and the other reagent, and put all these steps together. So it makes it more complicated. I'll probably skip over this, but just to say, enzyme immunoassays are almost ubiquitous. They're used in so many different analytical examples, and you can tell that because the process of doing an enzyme immunoassay in a microplate is actually about 45 years old since it was first done, and there's been a relentless increase in the number of people using this technique, so it's not gone away. Lateral flow is an example of an immunoassay. It's not an enzyme immunoassay. It's still nowhere near as commonly used as an enzyme amplified immunoassay. So how do we deal with this problem that we've got to put lots of different steps together? And by the way, lots of different people have developed lots of different microfluidic systems for doing this. Our unique angle is to try and focus on doing it as simply as possible, to make the simplest, most accessible, most inexpensive method. We developed this kind of cunning trick of fluidics, which we've named after swan because it looks a little bit like a swan beak. Maybe it doesn't. It does to me. And the idea is that we're just slightly modifying the strip by twisting it around and putting it vertically. What that allows us to do is to put the blood sample and the reagents through, and it's easiest to see in a video. So this is a nice video we have. And what you'll see is you've got to pretend there's blood in that. In a moment, what will happen is the blood will be washed away simply by the force of gravity flowing a washing reagent. You can see these tiny red lines, they're disappearing. And that allows us to remove everything in the blood that we didn't want and just stick the thing that the target that we're measuring. So then if we move it to the next step, you can see you can then put a detection reagent. So this is your enzyme conjugated antibody. So it's just one example of how people, people across the world working in the microfluidics area are trying to work out clever ways. We think this is very clever. It's a very simple way. It doesn't involve pumps or machinery or modification of the equipment to try and do this stepwise process so that we can get the enzyme amplification. And you can see this sequential process. It took us a long time to kind of pin down exactly what the steps were and work out different ways of delivering it. The dream is to come up with something that's nearly as simple as a lateral flow test. The advantage of the enzyme amplification is that you can detect things which are probably 100 or 1,000 times less concentrated. So you can expand the range of things that you can measure. So that's the system that we've developed for immunoassays. We've got this sort of major multiple advantages. And of course, if you're interested in immunoassays or microfluidics, we can talk in a lot more detail. But as I said, I wanted to use this as an excuse for talking about other things. So the technology we're developing, we're developing it for immunoassays. We're also developing it for blood tests, as John suggested yesterday, looking at things like coagulation pathway. We've also got a major program looking at analytical microbiology. A slightly different problem there. We're looking at bacteria, and we're not looking at blood samples at the moment. We're looking at urine samples. And with this immunoassay platform and the microbiology platform, we've done a lot of work to optimize the system. And we've now got to the point of starting to test whether the technology works in real samples. For the immunoassay systems, we've been able to complete a very clear set of validation with clinical samples, which shows that the technology does work in real samples, which is tremendously exciting. It's really good progress. We've been working on that for a long time. We've now got the funding to do the same thing for our urine microbiology test, which is what Sarah's been doing, which is very good progress, and it's very exciting, and it's exciting times. We do have some very specific challenges. One of the things that's great about our system is, I said at the beginning, is we can mass produce this. We can make 10,000 meters, which means we can do a really large number of experiments. So this afternoon after the meeting, Sarah will pop off into the lab and she'll set up an experiment. And in her experiment, she'll have quite a lot of different conditions. You know, you could do some sums as to how big the experiments get quite quickly. Because the material is really cheap and available, we can put lots and lots of samples together. We end up with an image that looks like this, or an image that looks like this. These are pictures taken by Ria and Sarah. Each of these images has got a lot of different, each of those little lines in there is one condition. And then what we do is we video over time. So we end up with 100 time points. So you can imagine that then you've got quite a lot of photographs, and each photograph's got quite a lot of information in it. And then what we sadly do is I get these poor people to sit down in front of a computer and measure the color intensity of all these lines manually. I can see Gemma's twitching there because she's done this as well. And essentially what that means is we throw away most of the data. And it's really interesting. If you look in detail, if we look at just one time point, we can see something really interesting happening where bacteria are growing in these capillaries. Just for a short period, you can actually see the individual bacterial colonies growing. So you could count the number of bacteria in the sample if you analyze that, but we don't do that at the moment because it's just too hard to wade through this data. So we know there's a really good opportunity there for analyzing this data using some machine vision and computer techniques. So there's a kind of plea out there to anyone who's got that expertise. There's a trivial thing of extracting information from the test, but then there's a bigger thing that we've also seen with the previous talk and externally, that once you've got the test results, you've then got to make sense of them, those results. And what's really nice about the system that we're using is because it's mass produced, we can actually do large scale experiments, we can generate large data sets. And so this is why having this mass produced extruded material is really beneficial. As a side, we also use cheap microelectronics. We don't use a smartphone most of the time. We use these things called Raspberry Pis, which is basically the smartphone computer and the smartphone camera that you can buy for 50 or 100 pounds. So we're measuring the data using a very inexpensive readout. So I would argue then that miniaturization and microfluidics absolutely does make it possible to make portable, disposable bioassays, which is great. And pretty much all the tests that I can imagine that you might want to do on blood, somebody somewhere has done in a miniaturized microfluidic system. So then the big question is, why are we still doing most of our tests in the lab? Even I would say that our example demonstrates that you can even make mass-produced microfluidic devices. One of the problems with a lot of the research in microfluidic devices is every device is handmade. You can buy commercially fabricated microfluidic devices. Typically, their list price is about £40 per device. So we can do quite a lot more than that by using mass manufactured devices. But you've got to always look at these statements and see where is the gap, where's the problem. And to me, it's that problem about prototyping. So the proof of concept phase is coming to an end. We know that we can make these measurements, but there is a huge gap between somebody in the lab doing an experiment showing they can measure something and having a commercially available mass-produced product. So that is a really important thing. So yes, we can mass produce this, but we're not making products. We're still before the stage where we have a product. And actually one of the big problems with that is that we genuinely don't know what we should be measuring with our multiplex measurements. We did our demonstration looking at dengue fever, but we were measuring dengue fever markers which don't have a clear clinical benefit. So we can't commercialize that. Even though we validated the system works, the actual test we did isn't necessarily a product in itself. So I think we can learn a lot from what's happening at the moment. I think there's a huge amount to be learned from testing in the COVID pandemic. One of my favorite examples of that is if we think about the power of point of care devices. So we have things like DNA Nudge and LAMPOR and various different point of care PCR machines, which are tremendously successful, the development of which has been accelerated by massive investments by people like the UK government. So there are now machines that do PCR tests, but also almost every single COVID test done by PCR in this country was done in a lab. And most of the samples were stuck in some kind of box and posted to the lab. So actually we shouldn't underestimate the power of posting samples, because clearly that's still better. And so this is where we are, and this is where I think this network is really exciting, because we can start to identify what are the barriers. And there's product delivery barriers, and there's also adoption barriers, so getting the uptake. So I wanted to come back to my starting picture. This is why point of care is so compelling. We all agree that we want to do blood tests instantly by the patient, by the clinician, point of care. So again, we need to look really closely and see what is the cause of the problem. And it's taken me a while to work this out, but I've highlighted in red quite a few steps here, which is supervised by experts when you have the traditional patient pathway. And somehow your point of care product, your COVID test that you get in a bag, somehow that has to replicate all of these different stages. So you need to make sure that you've got the, we talked yesterday about the capacity for biomedical scientists in labs. We don't have enough of these experts, but the experts do a really important job. They do really trivial things like calibrate the machines, make sure the test results are accurate. If you have a point of care product, which is standalone, it has to do all of that itself. And that's not easy to do. So from a product manufacturing perspective, I mean, it's a bit like autonomous cars. It's that kind of thing where it sounds trivial to get a car to drive itself, but is it really truly autonomous? So we can also look at this solution. So the solution is we're going to combine microelectronics with microfluidics, which again, I think is compelling. And us and many other people have done experiments to prove that you can do this, but we should look really closely at what's the difference between microfluidics and microelectronics. One really big difference is the consumer economics. So smartphones are not easy to make. It's just that people buy a lot of them. So even though a smartphone might cost me £150 or something, which is amazing, that only works because there are, I don't know, 100 million identical handsets being bought for £150. And for a lot of these clinical tests, it's actually hard, you do the maths, it's hard to work out that there'll be enough tests made to justify that economy of scale. So that's the first thing. The second thing is that our smartphones are essentially toys by comparison to medical tests. If they go wrong, what's the problem? You know, you get late for your meeting, or you don't get your WhatsApp message, or your game crashes, big deal. But if it's a medical test, that's not acceptable. And I don't think that regulation is a barrier. Regulation is there for a very good reason, to keep us safe. So we shouldn't burn the red tape, because we'll end up with diagnostic tests which don't work. So, and then the third problem layered on top of that is we've got all this biological complexity. So these are the things we just need to bear in mind. And I said at the beginning, we want to measure panels, and we're still struggling with panels of biomarkers. This is a beautiful study looking at dengue fever. The dengue fever is a very important infection across the world. It affects more than half the world's population. In endemic areas, everybody by the age of 10 will have been infected once by this really quite nasty mosquito spread disease. The big problem with dengue is that only a few people will get severe dengue, but the problem is that people who get severe dengue might die, and they might die in about a day. So they go from being really ill to just dead. So we've got to stop these people. All we need is a biomarker panel that will identify the people who need hospital treatment, and then we'll sort the problem. But this is a biomarker analysis with lots of biomarkers. You can see visually there's not much difference between the severe dengue and the not severe dengue. So it's very hard to, you can definitely see that the severe patients are different, but it's going to be really hard to translate that into a quick and easy test that says you need to be hospital treated, you don't, because of the difference between the sort of turquoise and red gap. So that's just one example from a really nice study. So even the identification of biomarker panels has still got some way to go. So I can say in the sort of biomarker area, you've got to translate the discovery study into real patients. This is what we were hearing about with real patients earlier. You've got this limited separation between the disease and the healthy. And then the most important thing of all with all diagnostics is what are you going to do about the results? So you've got to connect your product with reality. Another big problem, just by the by, all of these blood tests or other tests have got to be done on some kind of biological sample. So we've got to work out how to process the sample. Collection of blood still involves a phlebotomist. You still need to put a needle in somebody's arm, or you can use a finger prick, but that raises other problems. And then, of course, you've got this problem of autonomy. So when you have a point of care test, instead of having an expert doing the test, you have your instructions. So we've been working on that as an aside, just to try and improve the quality of instructions next to a test, and that makes a big difference. So if you have good instructions when you're doing a test at home, you're much more likely to have accuracy. So here's the question: is the future of clinical diagnostics in your pocket? Yes, maybe, but there's a long way to go. So we can take instruments, we can miniaturize them, but we just need to be a little bit cautious. It isn't that trivial to replace a lab test, but we'll keep on working on it. So thanks to all the brilliant people who've done work, including, of course, Sarah and Rui here, and Gemma as well, and we've worked with lots of other people. And thanks to funders as well. And with that, I thank you for your attention.